This is a final run through of all the topics that you need for the higher tier of AQA GCSE Combined Science Physics Paper 2 in 2022. In other words, I'm missing out the 3 topics that are in the not assessed section, and also the only required practical I've talked about is number 21, which is the one that's listed in that advanced information. Anything that's been listed as a major topic, I've put all the information on a green slide, and so any topics that are on lilac slides are topics that could still be assessed, but that should only come up as low tariff questions, so you do still need to know them, but they're not the major focus of your revision. I also won't be going through all of the equations in depth because you will have the equation sheet. By now you're hopefully aware of all these things, but just a final reminder that you do need to be writing in black pen and stay inside the box because your exam paper is going to be scanned. You need to watch out for any sneaky unit conversions, particularly for this paper, masses which might be listed in grams instead, and distances like lengths which could also be in centimetres but also in nanometres or micrometres or anything like that. For any kind of extended response, it's absolutely encouraged to give your answer in the form of bullet points because it will save you time and make your answer clearer, and there aren't any marks in GCSE Science for writing in full sentences, even for the 6-mark questions. If you have a question that asks you to evaluate some data, you need to try to add some value by making comparative statements like greater or lesser, and you need to write a conclusion to your answer because this is always worth a mark or 2. If you write a method, say for a required practical, make sure that it flows logically and that somebody could follow it in order to get the data that you're being asked to collect. Remember that your working scientifically skills are going to be assessed, so this is going to be identifying the units, knowing the difference between repeatable and reproducible data, being able to talk about the resolution of your equipment and how computerized methods of data collection are generally more accurate, rapid and sensitive. And don't forget that if you're translating data from a table into a graph, it's really important to make sure that you've plotted all of the points, even if one of them is at the origin or 0, 0. And remember that when your maths teacher says that a line of best fit has to be straight, they mean in GCSE maths, not in the real world, including science exams. So if your data does curve, then make sure that your line of best fit does too. With up to 30% of the marks on the paper for mathematical skills, it's really important that you've made sure that you're comfortable with all of these, as well as all of the more traditional physics content. This does include things like substituting and rearranging equations, but also things like standard form, giving your answer to the correct number of significant figures, and also plotting graphs. You can find a full list of everything you could be assessed on in Chapter 9 of the specification, but just make sure you've had a quick look at this list before the exam and that there's nothing in there that's going to completely throw you. While in 2022 you have got a bit of a helping hand and that you are going to be given all of the physics equations, bear in mind that these are all going to be in a single format. So if you're not very comfortable with rearranging them, then it's worth also learning some of the rearranged versions. Also, you aren't going to be given any indication of what the units for any of these quantities are, so you still need to be confident picking out the right equation. And sometimes a question will just give you some numbers with the units after them and it won't tell you what they are. You need to be able to translate that information. So it's worth taking a minute as you start the exam to just quickly scribble down what all of these quantities are measured in. You're not going to need every single equation, there's only about 8 of them that you're expecting to turn up in paper 2. But the ones that you should know are that all forces, including weight, are measured in newtons, and all masses for using these calculations need to be in kilograms. So watch out for that because it's very likely that the exam board will give you a question where the mass is given in grams instead and expect you to convert. Now for this first equation, the units for gravitational field strength are quite nice because as long as you have the equation, you kind of have the units. We can rearrange this first equation to be weight over mass is GFS, and so if we take the units for weight, which are newtons, and the units for mass, which are kilograms, and do newtons divided by kilograms, we get newtons per kilogram. So you don't really need to remember that one, you can work it out. Work done is a kind of energy, so it's going to be measured in joules. And all distances, so that includes distance in the second equation, but also extension in the third, and also wavelength in the 14th, are measured in meters. You can see from this that work done in joules, those joules are equivalent to a newton meter, a newton multiplied by a meter. For equation number 3, rather like equation number 1, you can work out what the units for spring constant are going to be if you rearrange the equation. So we can see that spring constant is equal to force divided by extension. So if we take newtons and divide it by meters, we get newtons per meter. Speed and distance and time is a little bit of a tricky one because although there are standard international units, you could also be given different units and you just need to make sure you're being consistent with yourself. So usually we have distance in meters, speed in meters per second, and time in seconds, but just be aware that you could also have a question where, for instance, they give you the distance in kilometers and the time in hours, and then your speed would be in kilometers per hour. So you just need to be consistent with yourself. Acceleration is in meters per second squared, and remember that that squared is part of the units, so it doesn't mean that you need to do any squaring when you're calculating it. You're just going to do the change in velocity divided by the time taken. Momentum is another one that you can work out from the units that you've already got. So here you've got kilograms for mass and meters per second for velocity, and you're multiplying them together, so you get kilograms meters per second. Finally, you've got frequency, which is measured in hertz. Within physics, we like to separate quantities into scalar quantities and vector quantities. Scalar quantities are ones which don't have a particular direction, they just have a magnitude, or in other words, a size. So this includes things like temperature, energy, and speed. Then vector quantities are ones which have both a magnitude and a direction. So this includes velocity, momentum, and also forces. Vectors, including forces, can be represented by arrows, where the length of the arrow corresponds to the size of the particular force, and then the direction of the arrow tells you what direction it's acting in. We can use these to draw free body diagrams. The idea of a free body diagram is there's no sense wasting all of your time drawing a car or drawing a boat, so instead we have a small circle at the centre to represent the centre of mass, and then the arrows go off this, showing the forces that are acting on a particular object. All forces in the world can be split into contact and non-contact forces. Contact means touching, so a contact force is one that only exists if the objects are touching each other. A non-contact force can exist even when objects don't touch each other, but that doesn't mean it goes away just because they are touching. You still have a weight which is caused by gravity even if you jump out of a plane, so weight is a non-contact force. But we don't suddenly start describing weight as a contact force when you're stood on the ground. It can and does exist both when you're touching the earth and when you're not, so we always describe it as a non-contact force. We've just named weight as one example of a non-contact force. Electrostatic forces occur between objects with a positive and a negative charge. You also know about magnetic force, which allows magnets to attract materials that are made of iron, cobalt, and nickel. The four contact forces you should be able to name are friction, which occurs when objects rub together, air resistance, tension, and normal contact force, which is the force that objects exert in order to stop objects from pushing through them. So here, the book is pushing down on the table due to its weight, and then the normal contact force from the table is pushing back. Newton's third law says that for every action, there is an equal and opposite reaction. This means that forces always come in pairs, and there are four things that are always true about the pair. The first thing is that the two forces are always of equal size. So if we take our example just there of the book pushing down on the table, the book is pushing down on the table with a force that is equal in size to the force with which the table is pushing back on the book. This must be true because if the force of the book pushing down was bigger, then the book would fall through the table, and if the force of the table pushing back on the book was bigger, then the book would be levitating, and neither of those things is true. The second thing is that they must be the same type of force, so either they're both pushes or they're both pulls. You never have an interaction pair where one is a push and one is a pull. Thirdly, they're acting in opposite directions, so the book is pushing down and the table is pushing up. Finally, they're always acting on the other object, so the book is pushing down on the table is pushing back on the book. The words mass and weight are often incorrectly used interchangeably. Mass tells us how much matter or how many atoms an object is made from, so this square here is made up from 56 atoms. Mass is measured in kilograms, and the shorthand for that is kg. It isn't affected by forces, so your mass doesn't change because somebody pushes you or because you're experiencing air resistance. It also doesn't depend on where you are. Just because my dino has moved from the Earth to the Moon doesn't mean his mass has changed, because he's still made of the same number of atoms. Any object with mass entering a gravitational field experiences a force called weight, which is measured in newtons. Gravity doesn't just affect planets or other really big objects like the Moon, but the strength of a gravitational field is determined by the mass of an object. So because Earth is so much bigger than you are, Earth's gravity is about 10 to the 24 times bigger than yours. And you don't really notice yourself having gravity because the Earth's gravity is so much bigger. Now this is important because the stronger gravity is, the larger the weight of an object will be. And that's important because this causes changes in motion. So for instance, you've probably seen videos of astronauts jumping on the moon, and because their weight is small, because the gravitational field strength of the moon is smaller than the Earth, they can jump higher and they can jump further. So to link back to our earlier point, scalar quantities don't have a direction, they only have a magnitude. So mass is an example of a scalar quantity. Whereas weight is a vector quantity because your weight has a direction, it's pulling you down towards the Earth. Weight can be measured using a piece of equipment called a Newton meter. This contains a spring which stretches as a larger force is applied. This causes a marker to move, allowing us to read the size of the force. An object with a bigger mass also has a bigger weight, so it would trigger a bigger reading on the Newton meter. In fact, we can even go slightly further than saying that as one increases, the other increases. Weight and mass are directly proportional, so as mass doubles, weight doubles too. This means that if we plot them both on a graph, we see a straight line which passes through the origin, or 0, 0. You will have this equation listed on the equation sheet, but just be sure that you're confident identifying which number is weight and which number is mass by looking at the units. So if you have a number that has an n written after it, that's the weight, even if the question doesn't call it weight, and the number that's measured in kilograms is the mass. Objects never have one single force acting on them, even if the forces are basically invisible and we can't see them acting right now. If we try to use all of the different forces acting on an object to predict how it's going to move, this can be quite complicated, but we can often simplify these forces into resultant forces, which you can think of like an overall force. So basically what we're going to do is we're going to add up forces that are working in the same direction and subtract forces which are working in opposite directions. And this is going to make it simpler for us to identify what is going to happen to an object's motion. So for instance, my box here has two equal and opposite forces acting on it. So the resultant force is 0 newtons. And this means that the box is going to move in exactly the same way as if there were no forces acting on it at all. In the example shown by this free body diagram, I've now got two opposite forces pulling in opposite directions. And you can think of the right-hand force as being made up of 60 newtons, which is opposing the left-hand force, and then another 40 added on. So the overall force that's acting, the resultant force, is 40 newtons to the right. Similarly, if I have two different forces which are acting in the same direction, I can just add them together to give me the resultant force. Now, for the higher tier, you may have quite complicated questions where you need to draw a mathematical diagram in order to be able to split up non-parallel forces. So, for instance, we might have a question that tells us that I have 100 newtons thrust going from west to east, and then a 50 newton wind at a 64-degree bearing. This is why you must have a protractor for your paper 2 for physics. So the first thing I want to do is draw a scale diagram. Remember that for any vector, we can draw a diagram where the length of the arrow corresponds to the magnitude of the force. So, for instance, I might pick a scale here where I say that 10 newtons is equal to 1 centimetre. So I would draw one line that was 10 centimetres to represent the 100 newton force, and then I would use my protractor to measure an angle of 64 degrees, and I would draw a second line that was 5 centimetres long. Then I'm going to use those two lines to be two sides of a parallelogram, and I'm going to draw the rest of the parallelogram. I can then draw a diagonal across the middle of this, and that represents the single vector that represents the resultant force. And if I measure the length of that line, then provided that I've done my scale diagram properly, the length of that line will be able to tell me what the size of the resultant force is. In this example, my line is 13 centimetres long, so using the scale that I've originally decided, this tells me that the size of the force is 130 newtons. If the pair of forces are acting perpendicular to one another, then it may be possible to solve this using trigonometry rather than a scale diagram. But do watch out, because if the question specifically asks you to draw a scale diagram, then there will be working marks for drawing it, and you may not get them if you've solved it using trigonometry, although it could be a good way to check your answer if you have a little bit of time at the end of the exam. So we start off in the same way. We draw our scale diagram, setting our scale beforehand as something sensible like 10 newtons per centimetre. Then we turn this into a parallelogram, which in this instance, because they're perpendicular to one another, is just a rectangle, and draw in the diagonal. And by measuring the length of that diagonal, we can tell what the size of that resultant force is. You could then measure using your protractor to see what the bearing is. It would also be possible to solve this using Pythagoras' theorem and then work out what the inverse tan is in order to work out what the degree of the bearing is. Almost certainly the most challenging thing you can be asked to do in this part of the exam is to separate a diagonal resultant force into its perpendicular components. So a question might ask you about a force that is 2000 newtons at a 30-degree angle. So the first thing we need to draw is our scale diagram to actually give us that force. So draw a horizontal line and then use your protractor to measure the 30-degree angle. So at this stage I'm just going to draw a little line because I'm not really worried about the length yet, I just want to make sure I've got the angle there. Then I'm going to pick a sensible scale and make my line be that full length distance. Then I'm going to make my horizontal line the same lateral length as that diagonal. Then I need to draw a vertical line to the same height as the diagonal. And now I need to measure those and use the scale that I've come up with to determine the length. In order to describe how those resultant forces will cause objects to move, we now need Newton's first and second laws of motion. The first law tells us that when the resultant force on an object is zero, acceleration is zero. That doesn't mean that the object is stationary, it means that its motion isn't changing. So if it is already stationary, it will stay stationary, but if it's already moving at a constant speed, it will continue to move at that constant speed. Newton's second law of motion tells us that the acceleration of the object is proportional to the resultant force acting on the object, which means that if I push it twice as hard, it will accelerate twice as much, and that its acceleration is inversely proportional to the mass of the object. So if I have an object that is 3 times heavier, then it will only accelerate by 1/3 as much. This leads us nicely onto the force is mass times acceleration equation. So again, you are going to have this on the equation sheet, but make sure that you know the units and make sure that you understand that if you have an acceleration that is something like 10 meters per second squared, you don't need to square that 10, you just use that number as it's been given. The squared is part of the units, it's not part of the calculation. Also remember that acceleration is a vector, so in other words it's always in a particular direction, and that means that it can be a negative number, which would show you that an object is slowing down. You may be asked to complete estimations about speed and acceleration and forces involved in everyday road transport, so it's worth having some ideas in your head about what typical speeds would be, and bearing in mind that you probably know speed limits in miles per hour rather than meters per second, it's worth knowing that there's about half a meter per second per mile per hour. It's also worth being aware that cars tend to have a mass of around 1,000 kilograms and lorries tend to be about 40 times heavier than that. When a force causes an object to move through a distance, work is done on the object. So a force does work on an object when the force causes that object to be displaced. Again, you need to be familiar with all of your units because you may not be explicitly told this is the work. The next major topic is about how forces cause objects to move, or rather how they affect their motion. And we start off with distance and displacement, which often confuse people because they sound quite similar, because they're both to do with how far you're travelling away from a starting point. I like to think of it as distance is about the number of steps that you actually take, whereas displacement is about how long it would take you to get back home. So if we imagine that we're starting on a journey from the bottom house on my little picture here, and we're trying to get to the top house, but we're not going there directly, we're going to the house on the right and then back again. The distance is 800 metres, so it's taken me 800 metres worth of steps to do this journey. But it doesn't really matter that I've gone to the right and then gone to the left, because distance is a scalar quantity, it doesn't have a direction. Whereas displacement says, how far away are you from your starting point? So by ending up there, I've actually only ended up 400 metres away. And that's displacement, which is a vector and it does have a direction. Likewise, speed and velocity may seem quite similar because they're both to do with how fast you're moving, but speed is a scalar, which means that it doesn't have a direction, whereas velocity is a vector, so it does have a direction. So that means that velocity can sometimes be expressed as a negative number, and that would tell you that you are now travelling in the opposite direction to how you were travelling before. So if I run at 5 meters per second due north, and then I turn around and I run at 5 meters per second due south, my speed hasn't changed because I'm still running at 5 meters per second, but my velocity has. Although speed and distance and time do have standard international units like everything else, and we're often going to see questions which express these in terms of meters and meters per second and seconds, you should be aware that we can make these compound units for speed out of any units for distance and time. So for instance, you could have questions where you're given distances in kilometers and times in hours, and in that case we would expect the speed to be in kilometers per hour. You are expected to know some typical speeds for walking and running and cycling, so this is what these are. Acceleration is another vector quantity, and it's to do with the change in velocity. Now, you may not be explicitly given change in velocity in the question. It's much more likely that you're given a final velocity and an initial velocity, and you have to work out what the difference between them is. So for instance, you could have something like, I was cycling at 5 meters per second and then I accelerated to be cycling at 12 meters per second. So you'd need to see that the difference between 5 and 12 is 7. So that would be my change in velocity. And then I would divide that by time. Remember, acceleration is a vector, so again it has direction. So if you have a positive number, that tells you that you're speeding up in the direction that you're travelling, and if you have a negative acceleration, that tells you that you're actually slowing down. Again, you need to know all of your different units for all of the different components. Next we come to two different kinds of motion graph, and it's really important before you start answering any questions where they give you one of these graphs that you've identified whether you're looking at a dt graph with distance on the y-axis or a vt graph with velocity on the y-axis. Often the best way to answer these questions is not to think about having learnt general patterns, but to look at what is that graph actually telling you, so what has happened to the distance or what has happened to the velocity, and then just answering based on that. We can use these motion graphs to tell us about the motion of an object both in qualitative terms and in quantitative terms, so numerically. So if we think first of all just about the general shape of a graph, for a dt graph, where we have a horizontal portion, this tells us that the object is stationary. So I'd be looking at this and saying this object at point B is 3 kilometers away from the starting point, and then at point C, it's still 3 kilometers away from the starting point. So it obviously hasn't moved anywhere, therefore it's stationary. If we now look at the section from A to B, I can see that it started out at the starting point at 0 kilometers away, and it's finished up 3 kilometers away. So obviously it has moved. The fact that the line is diagonal tells me that it's moving at a constant speed. So it's not accelerating, it's not decelerating, it's just going at this one constant speed. And then if I look at the line from C to D, I can see that it's steeper, and this tells me that although this object is again moving at a constant speed, it's now moving at a faster speed than it was before. Now, in terms of numerical calculations, we know that speed is distance divided by time. So at any particular point on this graph, we can use the gradient of the graph to work out what the speed is. So for instance, if I wanted to calculate the speed from C to D, I know that I need to do distance divided by time. So I need to know how far it has travelled, not in total, but just between points C and D. So in order to work that out, I'd say it finished off at 12 kilometres, but it started at 3. So the change there is going to be 9. And then likewise for the time, we've finished at the 12-hour mark, we've started at the 8-hour mark, so that's going to be a difference of 4 hours. If I do 9 kilometres divided by 4 hours, I get 2.25. And because that distance and that time are in kilometres and in hours, my speed would be in kilometres per hour, not in metres per second. If the graph curves rather than being a straight line, then we know it doesn't have a constant speed, but we can still use the same calculation to calculate the mean speed over that entire portion. However, if you're taking the higher tier, then you should be able to draw a tangent and use that to calculate the speed at any particular point. Remember, your most accurate calculations are going to be when your tangent is as long as it possibly can be, so don't just draw a little stubby one, make it as big as you can. If you're struggling to draw a tangent that is accurately tracking the graph, what I tend to do is to put my ruler on top of the curve rather than underneath it. And particularly if you have a ruler that's not see-through, that can make it a lot easier to make sure that it's touching the graph in only one place. So here's my tangent, and you can see that it's just touching the graph at the time of 15 seconds. And then I want to do the change in y divided by the change in x. So here my change in y, I've gone from 1300 metres down to 400 metres, which is a change of 900 metres, and my change in x is 25 seconds. Even if I've forgotten how to calculate gradient and I've forgotten change in y over change in x from maths, I know that my units for speed are metres per second, so metres divided by seconds. So that tells me which way round my calculation needs to be. Metres divided by seconds gives me 36 metres per second. Now a VT graph looks a lot like a DT graph, the only difference being that instead of having distance on the y-axis, we now have velocity. So again, I think it's worth just talking yourself through what is the graph showing you and then working it out from there. So if I look at B to C, I can see that at point B, the velocity is 6 metres per second. So this object is moving. And at C, the velocity is still 6 metres per second. So it's still moving and it's still at the same velocity. So now I can say that the horizontal portion of a VT graph tells me that an object is moving at a constant velocity. If I wanted to show an object that was stationary, not only would that line need to be horizontal, but it would also need to be at velocity is 0. So in other words, it would have to be going along the x-axis. If the line is sloping upwards, this tells me that the object has positive acceleration and is speeding up. And if it's sloping downwards, then the object is slowing down. The steeper that slope is, the faster the acceleration. So I can say that from point C to D, the object is accelerating more quickly than it is accelerating from A to B. If I want to calculate how far the object has travelled, then I need to calculate the area under the graph. And I can use this using just my normal math skills of working out the areas of rectangles and triangles. You can think of momentum as unstoppability or oomph. We define it as the tendency of an object to keep moving in the same direction. Heavier objects have more momentum, and faster objects have more momentum. So if we put that together, then we get our equation to calculate momentum. And if you know your units for mass and velocity, which you probably do, then we can just put these together to make our units for momentum. You need to know that stationary objects don't have any momentum at all. In a closed system, momentum is conserved. In other words, the total momentum before an event is the same as after the event. This is true in a closed system, which means that over the course of an event, no matter and no energy gets in or out. We can use this to make predictions about collisions and explosions. So let's look at an example of a collision where one roller skater bangs into another one. If I know that my first roller skater has a mass of 75 kilograms and a velocity of 4.2 meters per second, then I can calculate that initially her momentum is 315 kilogram meters per second. Now, when she collides with the other roller skater, that same amount of momentum needs to be split between the two of them. In other words, they're not going to stop dead, they're both going to carry on moving. But because the momentum is split between the two of them, they're now going to move at a slower velocity than the initial roller skater was moving on her own. So let's say that I know that my second roller skater has a mass of 65 kilograms. That means that the two roller skaters' masses together comes to 140. So that total amount of momentum is now going to be split between 140 kilograms, and therefore we can solve this to show that their final velocity is 2.25 meters per second. So they're both moving, but slower than the initial roller skater was moving on her own. Don't forget that momentum is a vector, so it can have a negative value to show you that we're moving in the opposite direction. And this is important in order for us to be able to explain explosions. So when we say explosion, we're not necessarily talking about a bomb. We could just be talking about two objects moving away from each other. But if you visualize that bomb for a second, before it explodes, it has a momentum of 0 because it's not moving. But at the end of the situation, obviously things are moving. Now, the reason that this can be the case is that as long as you have something moving to the right with the same amount of momentum as something moving to the left, then the positive and negative momentum still add up to be 0. So if we now think about our two roller skating friends and they're stood touching and then they're going to push off each other and go in opposite directions like this, we can work out that our roller skater on the left has got momentum of 975 kilogram meters per second, and therefore our roller skater on the right must have minus 975. It doesn't matter which one I've made be positive and which one I've made be negative, just that one is positive and one is negative, so they still add up to 0. Then if I solve my momentum equation for the new mass of the right-hand person, I can see that we're going to have 65 multiplied by velocity must add up to be this amount of momentum, and therefore the velocity is going to be minus 15 meters per second. And really that makes sense. They're slightly lighter, so they're going to travel slightly faster, but we're still in a similar ballpark. Unit 6 is the waves topic, and we start off by saying that waves can either be transverse or they can be longitudinal. In a transverse wave, the oscillation or the vibration of the wave is perpendicular to the direction in which the wave is travelling. In a longitudinal wave, then the direction of the wave and the direction of the oscillation are parallel to one another, so they're going in the same direction. The ripples on the surface of water are an example of a transverse wave. Longitudinal waves show areas of compression, where the particles are close together, and rarefaction, where they're spread out. And sound waves travelling through air are an example of a longitudinal wave. You should be able to label a transverse wave to show peaks and troughs and wavelengths and amplitudes. So we start out with the undisturbed position or the equilibrium position, and onto that we can put our transverse wave. Remember, a transverse wave is one in which the oscillation is perpendicular to the direction that the wave is travelling. So my wave is going left to right, but my oscillation is going up and down. On this, I can label the peaks and also the troughs. So the peaks are all the highest points and the troughs are all the lowest points. And once I have these labelled, I can add in wavelengths. So the wavelength of a wave is the distance between two equivalent points on two adjacent waves. So I can go from peak to peak, but I can also go from trough to trough. You could technically go from one of the middle points of the wave, but it's really easy if you do that to actually accidentally only label half the wave, so I wouldn't recommend doing it. The one that people tend to get wrong is the amplitude. So remember that the amplitude is half the height of the wave. It's the maximum displacement of the wave from the undisturbed position. The other thing that you need to be able to identify is the frequency of a wave. So if this box represents 1 second, then there are 3 waves inside it. In other words, 3 waves have passed a point within a second. So the frequency is 3 Hertz. Linked to this is the period. So the period is the time taken for one wave. So if I've managed to fit 3 waves into 1 second, then the period is going to be 1 divided by 3. In other words, a third of a second. Again, we have another calculation, so just make sure that you're familiar with all of the units for all of the different quantities. Electromagnetic waves are transverse waves that transfer energy from the source of the waves to an absorber. All types of EM wave travel at the same velocity through a vacuum or through air. Electromagnetic waves form a continuous spectrum. In other words, there isn't something fundamentally different about a radio wave and an infrared wave. It's just that we give them slightly different names depending on their particular frequency and wavelength. So you can think of it a bit like how in a rainbow, there isn't one set point where red turns into orange, we just give it a slightly different name depending on its wavelength. Going from long to short wavelength or low to high frequency, the groups of waves are radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays and gamma rays. Within that visible light portion, we start with red wavelengths, which are the longer wavelengths, so you can think that infrared goes next to red, and then we finish up with violet colours next to ultraviolet. Our eyes only detect visible light, so we only detect a limited range of those electromagnetic waves. Different substances can absorb electromagnetic radiation, in other words, take it in and not give it back. They can transmit it so that it passes straight through them. They can refract it so that it changes direction as it passes through them, or they can reflect it so they can bounce it back. And the way in which they do this may vary depending on wavelength, which is kind of obvious when you think about it. So if you just think about the visible portion of the electromagnetic spectrum, if you have a red object, then that red object reflects red wavelengths of light, but it absorbs all the other wavelengths of light. Some of these effects, like refraction, are due to differences in the velocity of the waves in different substances. So in other words, the wave is travelling at a different speed if it's in a substance with a different density, and that's going to affect how it's refracted. You need to be able to construct a ray diagram which shows how a wave is refracted at the boundary between 2 different media, so 2 different substances. So the typical example that you've probably done in school is a wave, like a light wave, going from air into a glass block. So the first thing that you need to draw is the normal. So this is this imaginary construction line at the point where the wave is going to meet the change in media. And then we can draw in our incident ray. And of course, the angle of incidence is measured between that incident ray and the normal. So the way that I always think about this is there wouldn't have been any point in me drawing the normal if I wasn't going to use it. Therefore, the angle of incidence goes between the ray and the normal, not between the ray and the block, which is where people sometimes draw it by mistake. Now, if there weren't any difference in refraction at all, I would expect my light to just carry on travelling in a straight line, because that's what light does. But because this glass block is denser, what actually happens is that the ray is refracted towards the normal. So as you go into a denser medium, you rotate towards the normal. And then because this particular block is a rectangle, and so the two sides are at the same angle, when it comes out, I can draw a new normal, and I'm going to carry on with my wave moving parallel to the original wave. If I had something like a triangular prism where the sides weren't parallel to each other, then I would find that although there would be refraction on the far side, it wouldn't be the exact reverse, and therefore I might end up producing a spectrum instead. The reason that this refraction happens is that as the wave enters the more dense medium, it slows down. Now, if the wave is travelling perpendicular to the surface that it's passing through, then the whole wavefront slows down at the same time and at the same speed. So the whole thing just slows down and then speeds up together, and you don't see any refraction. But where it hits the change in medium at an angle, it basically pivots around that point. So it's a bit like if you imagine if you're ice skating, holding hands with someone, and then one of you suddenly stops, the other person pivots around them. The one required practical that's been named in the advanced information for this paper is about investigating how the amount of infrared radiation that is absorbed or radiated by a surface depends on the nature of that surface. So that could be something like, is it shiny or matte, or does the colour make a difference? So in order to test this, you're going to need a number of identical cans or hollow metal cubes. They need to have the same dimensions but different surfaces. So the surface that we're changing, say the colour, that's your independent variable, and we want everything else to be the same because otherwise we don't know whether it's the colour that's affecting it or whether it's something else. You fill the cans with hot water from the same kettle, so it's starting at the same temperature, and then you use a ruler to position an infrared detector at a consistent distance away from the can. So you don't want to have one situation where your infrared detector is 10 centimetres away and then for a different can it's 20 centimetres away, because that way you wouldn't get valid data. Then you use that infrared detector in order to take readings. You can also take the temperature as a surrogate for this, but the data just isn't as valid. If you're taking higher tier, then you need to know that radio waves can be produced by oscillations in electrical circuits. When radio waves are then absorbed by an aerial, they create an alternating current, and that alternating current has the same frequency as the radio wave. So the radio wave can itself induce an oscillation in an electrical circuit. Changes in atoms and in the nuclei of atoms can result in electromagnetic waves being generated or absorbed over quite a wide frequency range. So you already know from your Unit 4 stuff from Paper 1 that gamma rays originate from changes in the nucleus of an atom. Electromagnetic radiation can cause hazards, but how hazardous it is depends on both the type of radiation and also the dose. Obviously, if you're exposed to a larger dose, then the hazard is higher. Infrared radiation is basically what happens when something gets hot, so of course you can be burned by it. But UV radiation also causes skin to age prematurely, which is why you get wrinkly if you use tanning beds, and it also increases the risk of skin cancer. Both X-rays and gamma rays are ionising, and this can lead to the mutation of DNA and ultimately cancer. Electromagnetic waves are really useful, and you need to know what each portion of the spectrum is used for. So radio waves are used for both television and radio broadcasting. Microwaves can be used for satellite communications, like sending text messages, but also for cooking food in a microwave oven. Infrared radiation is used in electrical heaters, but also to cook food, and also in infrared cameras, which can detect body heat for things like manhunts in the dark when the police are chasing someone. Visible light is used in fibre optic communication, like broadband. Ultraviolet light is used in energy efficient lamps, but also in suntan beds. And then X-rays and gamma rays are used in medical imaging and also in treatments such as radiotherapy. The final major topic, if you're taking the higher tier of the combined science papers in 2022, is the motor effect. So this is telling us that if you take a conductor, something like a wire, and there's a current flowing through that conductor, and if you then place that conductor in a magnetic field, then the magnet producing that field and the conductor are going to exert a force on each other. Now the reason that this works is that as long as there's a current flowing through the conductor has a magnetic field too. So you've got the magnetic field of the wire cutting across the magnetic field of the permanent magnet. And so those two magnetic fields are going to interact, and basically there's going to be repulsion or attraction, and therefore the conductor will end up moving. So this is called the motor effect, and we predict which way the interaction is going to happen and which direction the conductor is going to move using Fleming's left-hand rule. So you need to hold out your left hand, and it has to be your left hand, so that your first finger and second finger are at 90 degrees to each other, and then your thumb is also at 90 degrees. So you're sort of 90 degrees in 3 dimensions. Now your first finger represents the direction of the magnetic field, which goes from north where your hand is to south at the end of your finger. And then your second finger represents the current. And it's important to remember that the direction of the current, we're talking conventional current here. So in Unit 2, in Paper 1, we talked about the fact that when electricity was first discovered, we didn't know it was electrons moving, we didn't know it was negative particles. So conventional current actually goes backwards to what's really happening. So just make sure that you're aware of that when you're orienting your second finger. And then your thumb shows you the direction of the movement. So the idea is that if you know the direction of the field and the current, you can predict the direction of the movement. Or likewise, if you know which way the wire moves and you also know the direction of the magnetic field, then you can predict which way the current is flowing or whatever. As long as you've got two of the quantities, you can predict the third one. Now, a typical exam question might ask you to explain something like, why is it that a wire will move when you put it in a magnetic field? So you need to mention the fact that the wire has a current flowing through it, because if it didn't have a current flowing through it, then it wouldn't have a magnetic field, and therefore nothing would happen. Then we need to talk about the fact that the magnetic field that is around the wire interacts with the magnetic field of the permanent magnet. And then the final thing is to say that because of the interaction of those two magnetic fields, there is a force acting on the wire. A motor is made from a coil of wire which is carrying current in a magnetic field. So here's my coil of wire, and as you can see, there is the current moving around it in a circle, so always moving from positive to negative. And this is placed in a magnetic field. So this is made either from a sort of U-shaped magnet or from two separate static magnets. So we have north and south. This is going to cause that coil of wire to rotate. And in order to make this rotation continue always in one direction, rather than flip-flopping back and forth between it, we need a split ring commutator. When the motor is turned on, the coil of wire is experiencing the motor effect. But because the current is moving around in a circle, so on the left side of my coil it's moving away from me, and on the right side it's moving towards me, the force felt by the two sides of that coil is going to be opposite to each other. So the left side is going to be pushed down, whereas the right side is going to be pushed up, and this leads to rotation. So that's it for the 2022 edition of the higher tier of Physics Paper 2 of AQA Combined Science. I really hope it's helped you to feel a bit more confident about the exams. If you haven't already, I'd recommend watching my Morning of Physics Paper 2 video for some last minute tips, and I'm wishing you so much luck for tomorrow.